Hello, I'm Brian.
I'm Lisa, and our presentation is on the dynamics of a three-dimensional force-stamped system, and we'll be showing you our model, recreation, and associated plots. So to start, I will kind of introduce what our goal was for this project. So we set out to recreate one of the dynamical systems mentioned in a 2015 paper written by Miyagi, Okamoto, and Craik, and we've created three different plots: a static plot of the particle's motion, vector fields, as well as an animated plot of the particle's motion, and the vector fields and animations will show the fixed points of the system. In this paper, they discuss three different cases, but case A in particular is what we're focusing on, because they describe it as rich, as it arises in mechanical and fluid dynamical contexts. So these are the three cases that they present. In case A, h is less than 0 and k is less than 0, and they say that there are three different chaotic attractors along with period doubling bifurcations. Case B is both h and k are positive. All orbits in B reach infinity, although the authors are unable to rigorously prove that the orbits are unbounded. And then in case C, h is negative and k is positive, and they say that there are only bounded solutions that approach either the fixed points or the limit cycle. But as I stated before, we'll be focusing on case A for our project. And this is the system that they present us with, and they explain that the parameters h and k are chosen such that 2h minus k is less than 0, and that's to ensure that the phase volume is contracted.
Alright, so we'll jump into all three cases, with this being the first example of h is negative 1.5 and k is negative 1. The authors recommend that we run this with an initial condition of 4, negative 6, and 0, and actually, as Lisa switches to the plot here, you can observe crudely a four-leaf chaotic attractor, which is one of the highlights of this particular paper. At least that's what they brand this with in the abstract, right? Of course, please ignore the irregularities at the edges because, well, it's just MATLab's OD45 not fully being able to render out all of those things. But yeah, clearly we can see that, and in the paper they explain that this is a result of a period doubling cascade, and as we increase the k value that we looked at in the previous slide, the limit cycle actually loses stability, and as it tends to infinity, the limit of kn actually is negative 1.0195, and this is the point when the cascade actually is predicted to end according to Feigenbaum's theory. And yeah, we'll scroll through some of the vector field plots here. We can see that there are going to be 2 spirals and 3 saddle points, with the origin always being a saddle in all 3 of these cases that we're going to discuss. And here's the video.
Alright, so next up, looking at example 2. In this case, we have h is equal to negative 1.5, k is equal to negative 1.1, and the initial condition that we're using here is negative 2, 3, and negative 1. For these, we will only be showing you the static plot as well as the animated plot, because in all three examples that we're looking at, we have the same number of fixed points, and they have the same type of stability where we have 2 spirals and 3 saddles, so we just didn't want it to be repetitive. But here we can see the path that the particle takes. And then again, this will be the animation of the particle's movement.
Of course, it's mentioned that the red stars represent the actual fixed points in the system as well.
And you can see in this case, the particle stays in the limit cycle for a little and then falls out, but then comes back into it.
Alright, so the final example that we have here has an h value of -2 and a k value of -1.125 with a recommended initial condition of -1, 5, and 0. And this is one of my favorite actually shapes of all those three because it looks like a horseshoe, and this is actually a more classic example of a limit cycle. And the authors actually discuss the reason why this happens as well in the paper. They say again it's because of a period doubling cascade. And the variation in parameters, actually, we couldn't show you all the parameters for which we tested, but in the paper they show that successive period doubling bifurcations do happen. And when we sort of take the limit of the nth bifurcation, or limit for the nth bifurcation, we get a result that's really close to Feigenbaum's constant as well. We'll let the video play.
And that concludes our presentation. Thank you so much.